Today we're going to be talking laboratory fume exhaust systems. So thank you to all that have joined, and thank you to everyone who's joined on our previous sessions. We're going to go ahead and do our few housekeeping items. We have everyone muted and cameras off, so please ask your questions in the chat. I'll be keeping an eye on those, and if I can answer the questions, I will. Otherwise, I'll either interrupt Justin or hold the question to the end if it makes sense. As always, everything you see here, we can give the same presentation to your individual firms. We're happy to take groups up to Greenheck if you want to see some of these fans in person. We love talking laboratory exhaust, and I think Justin, who will be presenting with us, knows I absolutely love talking lab exhaust, so much so that I occasionally steal his thunder during our factory trips. But hopefully he knows that means I'm just passionate about these systems. So with that, Justin, give yourself an introduction and take it away.
Sounds good. I will do just that. So first and foremost, thank you everybody for hopping on this call. I know it's not easy, always setting some time aside throughout the day. So me at Greenheck, and I know the Dorse team definitely really appreciates it. My name's Justin Zahn. I'm an application engineer at Greenheck. My main job is to work on our laboratory and fume exhaust line. I am a part of what we call our FETI business unit. So that stands for fume exhaust tubular inline. I also do a little bit with our ductless garage transfer fans, and I also work a little bit on our data centers as well. So with that, we will get going. Kind of talking about a couple of the objectives today that we would like to cover. One is going to be the lab exhaust system guidelines. So I think it's very, very important to understand lab theory before we actually, dive into the lab products. I'm going to go over just some quick updates in the industry, and then also just give everyone, some fresh reminders on, just what to be mindful of when selecting a laboratory fan. With that, we'll go over the basics of operation then as well, and then we'll start diving into the laboratory exhaust products. So what is the main objective of a laboratory and fume exhaust system? We want to remove any effluent or contaminant from that space below and expel that up above that roof deck, okay? So the main goal of these systems is to get this plume or this exhaust up in a way far enough into the atmosphere where it's not going to be a danger to either the general public or to any building makeup air systems somewhere downstream. It's really important to remember, as I'm sure most of you know, most of the time, whatever these fans are exhausting is extremely hazardous to the general public and sometimes even deadly. So again, we really need to be, making sure that we are crossing our T's and dotting our I's for sure when it comes to how high this exhaust is going up in the air. So again, the whole goal, we want to get this up into the atmosphere so it's not a danger to the general public or to any building makeup air systems. So how do we design our lab fans? So we design our lab fans around one standard and one code in the industry. The first standard is going to be ANSI Z9.5. So what that states is the discharge velocity, so the air coming out the top of these fans, needs to be moving at 3,000 feet per minute or more. Typically, if you are trying to achieve a higher plume height, the velocity is going to be much more than 3,000 feet per minute. Okay, so it's really important to remember that velocity and plume height have a direct relationship with each other. Why that's so important to remember is this standard, ANSI Z9.5, for those of you who are familiar with this, this standard is essentially no longer existent anymore. It is now going to be up to you or whoever's in charge of that lab space to determine what kind of velocity you need coming out of these fans. So it's, again, when we talk about some of the effluents or contaminants that are coming out of these, we really need to be doing our homework on, what kind of velocities we truly need, because it's all going to come down to where these fans are going to be located, and again, what's coming out of these. So, we usually recommend sticking with higher velocities, just because we know it's safe, we know it works. But again, now you or your customer have that opportunity to essentially, change your velocity if need be. One of the reasons behind that, again, is kind of these fans are energy hogs, right? So they take a lot of energy to run. So the thought process is if you don't have to have your fans running at a higher velocity, why would you, right? If you can save a little bit of energy, you're definitely going to want to do that. But again, just be mindful of that. When you start messing around with that velocity, that's when your plume height's going to drastically drop off. So that's standard number one. Moving on to code number one. So this is NFPA 45. So this states that these fans have to be a minimum of 10 feet tall from the roof deck up. We will never sell a laboratory fan under 10 feet tall for a laboratory application. Reason behind that is because we don't want somebody walking up on that roof and having that opportunity to stick their hand, their face, or whatever else over these fans. On top of that as well, you're gonna notice our buddy sitting next to a couple of Vector units here, so a couple of laboratory units. Even for maintenance crews. So even the maintenance crews that know exactly what's going on up on that roof, we don't want them to have to worry about coming in contact with whatever's being exhausted either. So again, the whole point of this is just to keep people safe. With that being said, as I'm sure you guys can guess, architects, they don't really like us too much. They always claim we ruin their buildings with these fans. We think the fans are beautiful, but they do not. Okay, so it's a kind of a constant back and forth between us and them. But again, at the end of the day, our main goal is to keep people safe, and having this NFPA 45 code is a way to do that. All right, so moving on here now. We're going to talk about AMCA certification. So I'm assuming, or at least I hope most people on this call have heard of AMCA before. But for those of you who haven't, or maybe those of you who are maybe a little bit new to the industry, AMCA is that third-party testing service that ways to calculate or to say that you're AMCA certified. One quick second. I think someone's trying to call in. Oops. Okay, we're good. So moving on, again, talking about AMCA certification, there are two different ways to say you're AMCA certified. One way is incorrect and one way is correct. The first way is going to say you're tested in accordance with AMCA. So that could mean, again, that you're following AMCA's guidelines, but you're not licensed to bear this AMCA certified rating seal. So we see it all the time where customers will be working with different manufacturers in the laboratory world, and they'll hear that manufacturers say, "Oh, AMCA," or "We're tested in accordance with AMCA," or whatever it is, and it'll essentially go right over their head, which means that they hear the word AMCA and they essentially go blind and they think everything's a-okay. It's important to remember that's not always the case. You really want to hear a manufacturer say, we are licensed to bear this AMCA certified rating seal, or licensed to bear the sticker, or whatever you want to call it. It's very, very important you want to hear a manufacturer say that. And especially in the laboratory world, if their products are AMCA certified, they will be very proud about saying that. So again, it's just the whole point of this is just trying to decipher on, what is correct and what is incorrect on this. Because again, just because someone's tested in accordance with AMCA does not mean they are AMCA certified. So moving on here now, we're going to be talking about just best practices as far as stack design. So earlier we talked about the whole point of these fans is we want to, again, get that exhaust up and into the airstream as far and away as possible. And the way to do that is stick with straight stacks, nothing on top of these stacks. So the whole point of this is we do not want to negatively affect that plume height in any way, shape, or form. So if you look up here, again, straight stacks, nothing on top of the stacks. That's all the best practice, and that's usually what we want to stick with. But if we move down here to the bottom where it says pour should not be used, you're going to notice a couple of these stacks may have a cone cap on it or some other type of cover on it. We really want to avoid doing that just because, again, that is going to negatively affect that plume height. Sometimes people will get worried about rain entrainment into these systems, but it's important to remember that these laboratory units, they all have multiple different drainage systems. Okay, so if water does get into these fans for whatever reason, it's usually not too big of an issue, just because again, as long as those drains are unclogged, it works its way out. So with that, I also want to point out, if you look on the far right-hand side of the screen here, or I should say just the right-hand side of this pictorial, we really want to avoid using this gooseneck stack. Okay, I'm asking you guys from the bottom of my heart as a manufacturer, please don't do this with these laboratory fans. It completely defeats the purpose of what we're trying to do. So now, instead of expelling that plume or contaminant up, we are now going to be dumping that straight back down onto the roof or over the side of a building. Either way, it's not something that we want to do. So moving on here now, we are going to be talking about on how to calculate plume height, and there are two different ways that we can do that. The first way is through the modified Briggs equation. So this equation was actually used for quite some time, but is no longer recommended per ASHRAE. The equation that we want to use now is going to be the momentum flux equation. So the main difference between the momentum flux equation and the modified Briggs equation is going to be it's going to be the terrain categories. Okay, so the different terrain categories, this is going to be, where these fans are going. Are they going to be in the middle of nowhere? Are they going to be in a big city? That all has a direct effect on your plume height. And this equation takes that into account, and that is extremely important when it comes to these systems. So essentially, this momentum flux equation is far more accurate than the modified Briggs equation. But why I'm showing you this is because there are still some competitors out there that will use the modified Briggs equation. The reason why they use the modified Briggs equation is simply because using that equation will typically get you a higher plume height. Okay, so it becomes a sales tactic at the end of the day. They will claim, hey, even though we have essentially the same fan as Greenheck or whoever they're going against, supposedly our fan can, reach 5 to 10 feet higher of plume height. And at the end of the day, it's important for you guys to be able to pick up on that and say, that doesn't exactly sound right. It's important to remember that if you usually see a plume height that's significantly higher than another manufacturer, so let's say you were with Greenheck and you were looking at other options out there, and you saw one manufacturer that had 5 to 10 foot higher plume height, it's important to question that because they are usually when you see that, they are using the modified Briggs equation. And again, per ASHRAE, we want to use the momentum flux equation. So just something to keep in mind. And at the end of the day, this is not rocket science, right? These are fans. Doesn't really matter who you're going against. If you have the same style fan, same style nozzle, you should have, relatively close plume height. One shouldn't be significantly higher. So again, it's just something to keep in mind because it is something that we see a lot. I probably answer a question about this at least once every week. Once every week. So again, it's just something that we want you guys to be mindful of. So moving on, I really enjoy talking about this slide, mainly because this is something that is really specific to Greenheck's cap selection program. Most other manufacturers are not able, or they don't have anything like this within their selection program. So when we look at laboratory fans, we want to ensure, again, as I mentioned before, that plume is going up and away enough where it's not going to be a danger to anything downstream. Well, this ASHRAE plume concentration model that is available in our cap selection program showcases just that, essentially. So let's say you have a rooftop bar or maybe a building makeup air system somewhere downstream here. You can actually you can actually see how diluted the exhaust is going to be at this particular point downstream. Okay, so this is not a tell-all, be-all type of deal, but it is a very accurate estimate is what I like to call it. Obviously, different wind speeds and different weather conditions can all affect this. But again, on your typical operating conditions, this seems to be fairly accurate. And again, it's just more or less to kind of calm everyone's nerves a little bit. So if we do have a point of interest somewhere downstream that we are concerned about, we can simply type this information into our selection program, and it'll showcase how diluted that exhaust is going to be at that particular point downstream. So moving on now, talking about older lab designs versus newer lab designs. So it used to be that you would have, multiple different fume hoods, and then, or I should say, one fume hood per one fan. Okay, and that could mean you could have 20 to 25 different fans up on that roof. What does that mean? That means there's going to be a lot of maintenance required, right? That means there's going to be, a lot of different fans up on that roof, only serving, one hood, which doesn't really make much sense if you think about it. So nowadays, what we've gone to is through the manifold exhaust system. So the manifold exhaust system, you have multiple different fume hoods, all going up into some type of common ductwork. And now instead of having 20 to 25 different fans on the roof, you maybe would have 3 to 4 larger fans on that roof serving all these fume hoods. So it's going to be far less maintenance, which is good. That being said, we did keep a couple of fume hoods off here to the side, just to remind everyone on this call that fan manufacturers, we are not chemists. We don't know what chemicals to mix and what not to mix. So there may be times where you have to, you'll have a couple of bigger fans off to the side here, and you may need 1 or 2 smaller fans that are still servicing separate fume hoods, just because, again, you may not be able to mix those chemicals. So it is just something to think about. People ask all the time, again, what chemicals can you mix and what you can't mix? To us, the fan manufacturer, and again, we simply don't know. We really have no idea. We can tell you how well our fan's going to hold up to certain chemicals, but as far as what chemicals can mix and what you can't mix, that's going to be something that you guys are going to have to figure out on your end. But this is just a nice friendly reminder that we want everyone to essentially be doing their homework and just staying safe in these types of systems. All right, so now looking at the lab as a whole. Okay, so each lab has 3 control loops. The first control loop is going to be your face velocity, or your hood velocity of these fume hoods, typically around 80 to 100 feet per minute. You usually won't see anything too much faster than that. If you do, you run the risk of ruining whatever you're working on in this space. So 80 to 100 feet per minute is typically what we see. That's control loop number 1. Control loop number 2 is going to be how you pressurize this space. So typically this is going to be a negatively pressurized space. You will run into different situations, mainly OR suites or maybe special types of isolation rooms that will be positively pressurized, but it's usually going to be a negatively pressurized space. Control loop number 3 is going to be our duct static, and how we control that is through our bypass air damper. So it's important to remember that most of the time, these fans are going to be a constant volume system. Okay, it's the space below that's going to be variable volume. So these fans are going to have their set targeted performance point, which means they're always going to be trying to hit that set targeted performance point. So what does that mean for us? As that demand changes from this space below, it's our job to entrain some outside air. Depending on, let's say people are going home for the night, hood shut down. As they shut down, that duct static kind of becomes out of whack. So in order to release them that duct static, we will essentially modulate this bypass damper open. And as we do, obviously air comes in through there, which also helps us maintain our set targeted outlet velocity. Okay, so these fans are usually always going to be running. There are situations where they will not be, I would say, a constant volume system, meaning, let's say you have a high school lab, for example, someone's in that space, fans on, someone's out of that space, fans off. Probably wouldn't need a bypass damper at that particular point. But again, most times I always recommend having a bypass damper, just simply because I call it the safety net of the system. So if something happens that's catastrophic down here, we are able to always fall back on that bypass damper in order to ensure that we are still going to maintain our set targeted outlet velocity. All right, so now talking about pre-engineered versus built-up systems. It's no secret, we understand that these fans, they are expensive. We get that, we know that. So there are times where we see customers wanting to essentially shave some cost off by going with the built-up system. So for those of you who don't know what a built-up system is, you're basically taking different bits and pieces from third parties in order, and that's how you create the system, essentially. So you're taking different bits and pieces, putting them together, and that's your system. There's again, there's nothing wrong with that per se, if that is the route you want to take, but there are a couple of major obstacles that you may need to overcome. One is going to be the fan performance, right? You really have no idea how this fan is going to perform once it actually gets out into the field, just simply because it was never pre-tested before it actually left the factory. Okay, so that's going to be your biggest downfall of it. You could run into some performance issues with that as well. You're going to notice that this fan has guy wires. It's important to remember that these lab fans come with a wind load rating of right around 125 miles an hour without the use of guy wires, but that's if you use our curb. Okay. I'm not even sure if you would call this a curb. I'm not exactly sure what this is. But again, needless to say, guy wires were definitely required on this system because this is definitely not any manufacturer's curb. Looking at the pre-engineered system. So the pre-engineered system, again, the biggest advantage here is going to be that you know how these systems are going to perform once they actually get out into the field. Especially when it comes to a laboratory system, you always want to make sure that you are trying to eliminate as many headaches as possible before we actually, get these fans out into the field. Well, having these fans as a pre-engineered system is a way to do that. With that being said, you can also see there are no guy wires that are going to be required on these fans simply because we are using the manufacturer's curb or our curb in this case. So these fans much bigger, but yet no guy wires, and they all have that wind load rating of 125 miles per hour. All right, so now diving into the actual products themselves here. So we're going to start with our Vector H. Okay, so this is going to be our smaller laboratory offering or laboratory fan offering. These fans are capable of doing right around 24,000 CFM up to about 3.5, 4 inches of pressure. Still have that 125 mile an hour wind load rating without the use of guy wires, and then you have belt or direct drive construction. I want to spend a little time on this direct drive construction. So this is going to be the fan that's furthest on the right here. You're going to notice that this motor is actually kind of floating here on the outside. That was done on purpose, just to showcase to you that if you ever need to get into this fan for whatever reason, you would simply pop this panel off, and as you do, the motor and the wheel would actually all come out as one assembly. So this is what we call our power pack. So it's a really nice design point. We call these direct drive Vector H's plug and play type of fans. Really easy to set up, really easy to maintain. And then on top of that as well, the fan as a whole, this direct drive Vector H fan as a whole actually really sets us apart in the industry from all of our competitors. As of right now, we are the only ones in the industry that can offer this small of an inline laboratory fan in a direct drive offering. Okay, so none of our competitors can offer anything like this. I know they are trying to work on it. As far as how close they are to that, I'm not 100% sure. Sounds like they're a ways off, but again, right now, this is one of the, or I should say, this is the only this small of an inline fan in a direct drive option in the industry. So where would you use these fans? High school labs, college science labs, basically any job that doesn't require high CFM or high pressure, that is where you're going to want to utilize these types of fans. One application I want to put out and just kind of let you guys know about is restaurant exhaust. So with restaurant exhaust, we can actually get these Vector H's with a grease exhaust rating. Sometimes people would laugh at me when I say this, just simply because it really doesn't make much sense, in some people's minds that, to put a laboratory fan on a restaurant. But it's important to remember, the ultimate goal of these fans. One of the ultimate goals is to get that effluent or contaminant up into the air as far and away as possible. Well, as you're doing that, you're also getting the smell up in a way into the atmosphere. So, let's say you live next to your favorite burger joint, steakhouse, whatever that may be. It's going to smell good for a while, but you're not going to want to smell it every single day of your life. That's where these fans come in. Not a huge demand by any means, but again, we just want to let people know, hey, we can utilize these fans for other applications besides laboratories. So moving on to the Vector MD. Okay, so the Vector MD, probably the more popular laboratory offering. M stands for mixed flow, and the D is going to stand for dilution. So the mixed flow is the type of wheel that's in these fans, and then the D is going to be the dilution style type nozzle, which we'll talk nozzle types here in a little bit. These fans are built for larger jobs, okay? So capable of doing right around 80,000 CFM, up to about 7.5, 8 inches of pressure, give or take. Still have that 125 mile an hour wind load rating without the use of guy wires. And we can also offer belt or direct drive arrangements in these as well. Couple key design features when it comes to these fans that actually set us apart from some of our competitors. One is going to be where this isolation damper sits. So this isolation damper actually sits above the bypass plenum. Why that's such a big deal is because a lot of our competitors will actually have this isolation damper within the plenum. And so what does that mean to actually get access to it? Well, if you're with one of our competitors, you'd actually have to crawl into a contaminated area in order to access this isolation damper. We've seen people actually have to crawl in with hazmat suits on before. It does not look like it's safe and does not look logical in our eyes. So what we did is we simply bumped this isolation damper up above our plenum quite some time ago. And now you're going to notice this bolt hole pattern here on the outside. All you would need to do is simply take this cover off, unbolt, and pull. Okay, so very easy to get at, very easy to maintain compared to what our competitors offering is. Then looking at the bypass plenum as a whole. So this is another thing that kind of sets us apart from our competitors. Looking at the bypass plenum, once you select, or I should say, one thing that changes the most on from when that first inquiry comes into us to when these fans are actually installed in the field is going to be where your inlet connection goes. Okay, so once you select side inlet with our bypass plenums, this whole plenum will essentially come sealed up and shipped to you. So what does that mean? You can essentially choose your inlet in the field. So if you ever need to modify your inlet for whatever reason, you could simply remove one of these panels. Hopefully you guys can see my mouse, but you would just remove one of these panels, hook up your ductwork, and you're good to go. Whereas if you were with one of our competitors, once you select your inlet, you really need to make sure that's where your inlet's going to go because you don't have that modification ability. Well, again, in our eyes, that's not logical. These systems are already complicated enough. We don't want to complicate them anymore. Okay. We have a saying at Greenheck that we want to be easy to do business with. We have an unwritten saying that, in the laboratory business unit that we want our equipment to be easy to work on. These slight design tweaks have allowed us to kind of achieve that. With that, looking at this direct drive offering, so a lot of people will think that this motor is within the Airstream. It is not. It's important to remember that all of our motors on our Vector fans are completely isolated from the Airstream, meaning they do not come in contact with whatever's being exhausted, including this direct drive Vector M. So this motor actually sits within a bifurcated housing where that air will actually move up and around that motor into the nozzle, into the atmosphere. Okay. Why that's really important to remember that, again, none of our motors are within the Airstream is because we get a lot of questions about explosion-proof motors. At the end of the day, 9 times out of 10, I would say that explosion-proof motors in these systems are just simply not needed, okay? Because, again, the only thing these motors are coming in contact with is fresh air. If you look at the direct drive offering here. So this is a nice little pictorial of that bifurcated housing. Again, that air would come up through that inlet bell right here, and you would be able to see this air move up and around that motor and then into the nozzle, into the atmosphere. So again, that motor is completely isolated from that airstream. Belt drive, same thing. Sits in that box on the outside here. Again, that motor does not come in contact with whatever's being exhausted. If you look at belt or direct drive offerings, so belt, again, sits in this box on the outside here, much easier to service, much easier to get at. But what's the drawback to belt drive? Belts, right? So more service is required. Whereas the direct drive, these fans come with 1-year lube intervals. So very little service. But the drawback to direct drive is going to be that when it comes time to actually get at this motor, it's going to be a little bit of a process. Okay, so it's not going to be as easy as it would be for the belt drive offering, but nonetheless, two options that you guys have to choose from. Looking at a couple of the configurations that we are able to offer, so anywhere from 1x1 to 6x1, to all the way up to 2x3, 2x2, whatever it may be. We can accommodate to pretty much anything you guys would want. These are essentially our standard offerings on here. But again, we have the ability to go to 7x1 or maybe even 8x1, depending on, what that job all entails. So looking at the Vector MH now. So same exact fan. All it is all we're doing now is simply changing out that nozzle. So this is going to be our high plume offering. That's what the H stands for. Still capable of high CFM and high pressures, but again, just changing out that nozzle, and we'll compare these two nozzles here in a little bit. So looking at the inline fans, the biggest pro when it comes to these is going to be you can have extremely large systems with a fairly small footprint. Okay, so you're going to notice our buddy standing here next to a couple of Vector units, some of our larger Vector units at that. Again, a large system taking up minimal roof space. Okay, so that's gonna be the biggest advantage to these fans. And then the cons, if you look at it, taller finish heights. Obviously, here's your average size man, and to get up actually close to these motors or up onto this system, it is going to be a little bit of a process. So it's just not going to be as easy as this next fan that we're about to talk about. So this next fan is going to be the Vector C. C stands for centrifugal, and that D again just stands for dilution. These are the fans we like to push most in the industry, and I'll kind of explain the advantages here in a little bit, but we like to use these on bigger jobs. So capable of doing right around 140,000 CFM, up to about 13 and a half, 14 inches of pressure. Okay, so they are built for really, really large jobs. Some of the pros, they're going to be slightly more efficient than your typical laboratory fan. Obviously, we talked about the pressure and large air volumes, but one of the biggest selling points is going to be where that motor is located, right? Right at rooftop level. Really easy to get at, really easy to maintain. But because these fans can get very large, that is, unfortunately, one of the drawbacks of them is their footprint can get very, very large as well. So with that being said, as the footprint starts to expand, there are times where it just simply, it eliminates the use of this style of fan on certain roof decks, just simply because we can't fit these fans on certain roofs. It kind of seems that roof space has been coming at a premium nowadays. And again, that kind of eliminates the use of a centrifugal style unit. But when we can, this is definitely where we like to start on larger jobs. So here's a nice pictorial, a couple pictorials of the large footprints. So anywhere from 1x1 to 3x1 to 4x1. Again, these take up a lot of space, especially if you have that bypass plenum included with that, or if let's say you have energy recovery included on that as well. Sometimes it just simply takes up too much space and you can't use it. So looking at the typical mixed flow and centrifugal applications. Pretty obvious. Any job that, again, requires high CFM or high pressure capabilities, that's where you're going to want to use these types of fans. All right, so now comparing the two different types of nozzles. So we talked about the dilution offering, and we also talked about the high plume offering. Before I start this, so when you would use each nozzle, right? So with a dilution style nozzle, that's mainly used for, to knock down a exhaust that if it maybe has a really bad odor or an exhaust that's really, really hazardous. This is a great way to knock that down a little bit. Okay, so you can actually get up to 218% more dilution by just utilizing this nozzle. Once you start introducing bypass air on the bottom here, obviously you can't see a bypass damper right now, but if you would introduce some bypass air into the system, then you're looking at well over 300% more dilution. Okay, so before I go into this again, I just want to emphasize the dilution style nozzle is definitely still 100% needed, but it's not always needed. So there's a common narrative in the industry that if it's a laboratory fan, that means you have to have dilution. Us at Greenheck, we are trying to change that narrative. It's mainly coming from our competitors, I will say, just because it's a dilution style or it's a laboratory fan, it's not meaning it needs a dilution style nozzle. Our competitors will say it has to have dilution mainly because that's the only thing they can offer on a lot of their fans. So what we did is we actually compared the two nozzles. So we selected a fan at 30,000 CFM and about 5 inches of pressure. We compared, multiple different statistics, starting with the brake horsepower. So the dilution style nozzle had a brake horsepower of 55.1, whereas the high plume style nozzle, so this nozzle over here to the right, had a brake horsepower of 43.0. So we're entraining more air, which means on the dilution style nozzle, that requires more horsepower. And as you can see, it's significant more horsepower. both of these fans are going to be doing the same exact thing as far as, the CFM that's actually going through them, and they're still handling the same amount of pressure, but the dilution style nozzle requires more horsepower. So it's not as energy efficient. Then we took a look at the effective plume rise. Okay, so the effective plume rise for the dilution style nozzle was at 50.4. We then took a look at the high plume nozzle, and that effective plume rise was at 54.0. Okay, so now we're not only saving energy with this high plume nozzle, but we're actually also performing a little bit better as well. Granted, some people could say that with that dilution style nozzle, you wouldn't need necessarily as high of a plume height because it is going to be diluted, but nonetheless, I mean, you're still going to be using more energy when utilizing that dilution style nozzle compared to that high plume nozzle. So this high plume nozzle, nothing too crazy about it. You're taking a large space and condensing it down into a smaller space, creating velocity. This is going to be, again, as you can see, the most efficient option when it comes to nozzle technology. And again, the big takeaway here is that Greenheck's we're not discrediting the dilution nozzle at all. But what we're just trying to tell you or your customers is that we want you guys to do your homework. Okay, so just because it says laboratory exhaust does not mean you have to have dilution. And if you guys remember nothing else from my presentation today, just remember there's no code saying you must have dilution because for some reason, people, again, they think laboratory fans, they think dilution, and that's just something that we are really, really trying to change in the industry. All right, so looking at accessories. So we're going to go over some of the things that we can offer on a couple of our fans. We'll dive into energy recovery a little bit. Energy recovery is more or less going to be a little bit higher level, just because this could be another whole hour to 2 hour presentation. So if you guys have questions, by all means, ask away. I can definitely dive deeper into the weeds, if need be. So starting off, we're going to start with our standard bypass plenum. So this is going to be nothing too crazy, obviously just a single wall construction when it comes to the plenum. This is really all you're going to need on most laboratory systems. The upgraded version of this is going to be the double wall bypass plenum. So the double wall bypass plenum, mainly used to prevent condensation. We've ran quite a few tests. We've ran quite a few tests on the double wall bypass plenum versus the single wall bypass plenum and how condensation, I guess really comes to be in both of them. And at the end of the day, they perform pretty close to both the same. Okay. One reason why we had this double wall bypass plenum is because our competitors can offer it. But just one thing to keep in mind with this is, when looking at the double wall bypass plenum, you're going to be adding a significant amount of weight to that rooftop when utilizing this type of plenum. So that is something you have to take into account for. Again, at the end of the day, most of the time that single wall is going to do everything you need it to do. But that double wall plenum is out there for you guys as an option. So looking at sound now, so there are multiple different ways to combat sound. Obviously, these fans, the nature of them is to be loud, right? I think on that screen before when we were comparing the two nozzles, one of them had a decibel rating of 91 and the other one had a decibel rating of 88. Obviously, both still really, really loud. So here are a couple of ways that we can combat that, essentially. So starting with the attenuated wind band and wrap, this is going to be used to reduce outlet sound on these fans. The best part about this is going to be you're not really adding any height to the system. So what does that mean? There's essentially, no guy wires become required. Obviously, not too many people want to deal with guy wires anymore. It kind of seems like they're becoming a thing in the past almost. So using this type of attenuation, you avoid the use of guy wires, whereas this next form of attenuation, so the inline discharge attenuator, this is going to be the best way to combat sound. Okay, so this is going to be, it's going to combat sound a little bit better than the attenuated wind band and wrap. But the disadvantage here is we're going to be adding height to that system, which means guy wires may become required. Okay, so that's kind of the trade-off between the two. If sound is a major concern, usually we see customers go with this inline discharge attenuator. But nonetheless, I mean, you guys do have two options to choose from. But there is also a third option. And this option is actually kind of where I like to start. So We talked about the bypass damper a little bit earlier on in this presentation, but we didn't go too much into detail. So a lot of people who are not familiar with um, laboratory systems, a lot of people will think that this whole weather hood essentially is the bypass damper, and it is not. That bypass damper actually will sit inside of this weather hood, and it is actually fairly small. And why it's so small is because once we modulate that open, again, we want to ensure we are creating velocity going through there. Well, the drawback to these bypass dampers being a little bit smaller is because it becomes one of the louder parts of the fan, right? So that is something that we have to take a look at. Well, one way to combat one of the louder parts of the fan, depending on how much additional bypass air you actually are planning on pulling in is through the inline bypass attenuator. Okay, so best part about this is, again, you're combating one of the louder parts of the fan and you're not adding any height to the system. But this really only makes a ton of sense if you're going to be pulling in a significant amount of additional bypass air. If you're not, it could still help combat sound, but just not as well as if you were, essentially pulling in bypass air all the time. But nonetheless, three options for you or your customers that you can choose from. All right, so now looking at the crane assembly or the jib crane assembly. So the jib crane just provides means to remove motors and or wind bands and elevated assemblies. Basically takes responsibility out of someone else's hands, puts it back into your hands where you're not waiting on a crane or anything like that to come out there. One thing about this crane assembly that I will say, one is it's only available on our Vector M's. Our Vector C's, you wouldn't need it considering where the motor's located. And then our Vector H's are just simply too small. Okay, so this will only be on our Vector M's. One thing I will say about this is going to be if you are unsure if you need a jib crane, so let's say you're 50-50 on if you want to add one to one of these laboratory fans, we always say at least order these sockets up front from us. If you do not order the sockets up front from us, you cannot install this jib crane later in the field. Okay. And the reason behind that is because these jib cranes can weigh anywhere from 300 to 400 pounds, all the way up to 600 plus pounds. So once you start adding motor weight to that or stack weight to that, if these sockets down here are not properly installed, it could become a safety issue for whoever's working that crane, which is definitely something that we do not want. Okay, so again, if you're on the edge, we always just say keep the door open, order those sockets with the fan. That way you can always add that jib crane later down the road. All right, energy recovery systems for lab exhaust. So this is definitely one of my favorite topics. Again, I won't go too much into the weeds on it, just because I know we're kind of running short on time here and I have a little bit more to get through. And I also want to be able to answer questions. But again, this could be another whole hour and a half presentation. So if you guys have questions, please by all means let me know, and I can definitely dive into this a little bit deeper. But stating the facts, right, of laboratory exhaust systems, they are energy hogs. That's the nature of them. We know that just again because they are running at such high velocities. It requires a lot of energy, and I think that's kind of common sense to think about it. And you also got to remember too, laboratories are 100% ventilated. Along with that, 50% of the energy used in laboratory is attributed to ventilation. Okay, so applying energy recovery definitely makes sense on larger jobs. Okay, so you wouldn't really want to apply one of these energy recovery systems on a smaller job. We usually see it, I'd say roughly around 25 to 30,000 CFM and up. Anything below that, it's just going to take a while to get that payback back. But again, we do have some options here for you guys. So looking at the energy recovery types. So with standard energy recovery systems, you would usually use a wheel or a plate in those types of systems, but that requires exhaust and supply airstreams to be co-located. That is not something we want to do in a laboratory system with energy recovery. Okay. You having a wheels or plates, you have that possibility of cross-contamination, essentially, of that supply and exhaust air. So what we do is we actually use the runaround coil loop method. So that it's supply and exhaust ducts, they're not brought together, so there's no possibility of cross-contamination whatsoever. Obviously, again, most of the time, whatever these fans are exhausting is really hazardous. It's not something you would ever want to mix with, fresh supply air. Here's your typical energy recovery setup. So looking at this, you have your runaround coil loop method. This is what we would supply. essentially. You can see the coils in there as well. With that, so our coils are coated in something that we call E-coat. It's your typical header site coating for those of you who have heard of that. So very, very robust. We actually just expanded our energy recovery line as well. So on our Vector M's and our Vector C's, it used to be we could offer up to 60,000 CFM. We can now offer up to 80,000 CFM for cabinet capacity as far as CFM goes. Again, it's kind of the way the world's turning. It's what we are seeing a lot of on, larger lab jobs. Energy recovery is at least mentioned on it once. So essentially, we just want to make sure we're always staying in the game when it comes to these energy recovery systems. So with that, earlier we talked about restaurant exhaust. We talked about, on that Vector H, on that smaller Vector H fan, we talked about how you can utilize these fans for other applications besides labs. Well, we have a couple of applications here that we're going to dive into that we see these fans utilized on quite a bit. So starting with diesel generator exhaust. So this is where, you may have big standby generators, and let's say buildings, or buildings such as professional sports arenas, hospitals, or whatever it may be. When this generator fires up, that exhaust obviously has to go somewhere, right? So what we have here is it's called our Vector CD diesel. And what it actually does is you're going to see the diesel generator exhaust come up below here, and we would actually use our Vector C fan, and we would open up this bypass damper here, and then we're also going to utilize that dilution style type nozzle in order to dilute that airstream a little bit more. This is essentially what it looks like. So that's going to come up, and then if you look over here to the side, it goes straight up. So kind of a cool video. I like showing people that. This is not a huge demand by any means. We see it every now and then. But again, just another application that we are able to utilize these Vector fans on. So we can actually go, it says 750 degrees or greater. We can actually handle up to right around, I believe it's 1,000 or 1,100 degrees through this, especially if you're introducing some fresh air through here, through that bypass damper in order to cool that down. Again, not a huge demand for this, but it's just something to, kind of keep in your back pocket just in case an opportunity ever comes up. Wastewater treatment. So this is a situation where we would utilize the dilution style type nozzle. So obviously wastewater treatment plants, they don't smell the best, right? Well, with utilizing this dilution style type nozzle, this is a great way to knock that smell down a little bit. It's something that we see from time to time again. But again, only the dilution style type nozzle would be utilized on this type of application. Emergency ammonia exhaust systems. So for those of you who don't know what this is, an emergency ammonia exhaust system is needed in any large refrigerant capacity. Okay, so let's say, I think the easiest example would be ice rinks, for example. So NHL hockey rinks, they have to have an emergency ammonia exhaust system. We do have a solution for that as far as being able to exhaust that. Not a huge demand for this, at least not on our end. There's a whole different list of codes that we could go through, probably have another whole 30-minute to 40-minute conversation on this. But just know, hey, we can supply a solution for this if it ever comes across your desk. So I think the big takeaway here is, don't just think lab when it comes to these style of fans. Think anything that, we need to get that exhaust up in a way we can utilize lab fans. So with that, is there any questions, or is there anything else I could dive into a little bit deeper? I wanted to leave some time for questions. I believe we have about 9 minutes left.
Did you even take a breath during that, Justin?
Nope. No, I don't think so.
That was wonderful as always. And in regards to the heat recovery plenum, that's a pretty big thing we see in the Pacific Northwest. Our state energy code, I think, calls for it above 5,000 CFM or a variable volume system with bypass and turn down, right? But with the decarbonization efforts and the high efficiency energy modeling we're seeing a lot of those heat recovery plenums We often see engineers design around third-party air handlers. And I think that's just because they don't realize Greenheck can provide that plenum themselves, and we can actually uh, do that plenum as part of the selection of the fans. So we know what our internal pressure drops are going to be, and our fans are selected to cover your external, and then we're selecting against our own. So that's kind of something a little different where you don't have to worry about the calculation from one vendor to another. We're selecting it all as part of one system. So that's a huge item in the pro column for going with the Greenheck ERS plenum.
Right. The pre-engineered system, right?
Yeah.
Yep, exactly.
So we're going to check the chat here and see if we have any questions. Maybe you just said everything so well. We've had pretty
Maybe,
good
or
engagement on questions so far, but
maybe I went too fast as well and I
yeah.
confused people.
Just know that the similar presentation you saw Justin do, we have a similar version ourselves at Dorsey, but it's always fun to have our manufacturing partners come in, and sometimes they drop hints about the latest and greatest of expanding certain offerings. So I always like hearing that. You can see some of these fans in person at the factory. They always like to joke around that the ones inside the showroom are the smallest sizes they make because they're the only ones that could fit in the physical room. And of course, they are massive. And they have some great cutaways too, where you can see some of those panels Justin was referring to for taking off and switching, whether it's a bottom inlet or side inlet. And then also your isolation damper access, which is a big thing. Well, all right. I guess with that, I don't see any questions. Thank you all for joining us. Join us next week for our introduction to Metal Air by Greenheck air distribution products. And as always, if you need anything with a vector system, you can get with myself, or if you're in the Spokane market, Blake Bonham, and I'm sure many of you know Scott Boucher in our Seattle office as well. So with that, Justin, appreciate it as always. And if any of you make the trip up to Greenheck, you can see Justin give this presentation in person with just as much energy.
All right. Thank you, everyone. Appreciate your time.
Thank you all, and we'll see you next week.